The model's CSV file that we are going to use in this example is the following. So we have two settings when we are not using models to create software. And this value A, represents the quality of the software that is produced. And the value ranges between 0 and 100. For the second setting, or the second group, when we use models to create software, we have this value B, which represents the quality of the produced software. And again, here the values range from 0 to 100. So this is the models.csv file that we are going to use to run the different tests. So let's open the RStudio, and first of all, let's load the data that we have from the CSV file into the tool. And we can do that following this command, and then I will also fetch the needed values and put them in these two variables. So when we don't use software models, what are the quality values? And also when we use models, what are the quality values? So let me just run this piece of code, and as you can see, we have the data in our tool. As you can see, we have 25 observations for each setting. We can plot a box plot to see the distribution of the data, and I can use this command, of course. And this is the result of the plot. As you can see, on the x-axis we have the two settings when we are not using models and when we are using models, and on the y-axis I can see the quality of the produced software. And if you remember the box plots here, this line here at the bottom represents the minimum value, the one here represents the maximum value. The area here in gray, the rectangle, represents the interquartile range, which is the difference between the third quartile and the first quartile. And the line here, the thick line here, represents the median value. Very good. So we can also calculate the means and the standard deviations. So I will select this piece of the code. So we will get the means and the standard deviation for each one of these groups. I will run these codes and we will get these results. So the mean value when we are not using models, this is the value of the quality, 65.906. And when we are using models, the quality average or mean is 82.254. As you can see here, this number is higher than this number. So we already observe a tendency that the quality of the software is better when we are using models. Very good. So let's check the assumptions to conduct the test. So first of all, we check the test of normality if the data are normally distributed. So we run the Shapiro-Wilk test for the two groups. I will run this line of this piece of code. So for the first group, when we are not using models, the p-value is 0.1166, which is greater than 0.05. And this means that the data here are normally distributed. For the second group, when we are using models, the p-value is 0.5575, which is again greater than 0.05. And this means also the data in this group are normally distributed. So we have satisfied the first assumption. And then we go to the test of homogeneity of variances. So I will run the test, the Fisher's F tests. And this is the output of the test. As you can see, here we look at the p-value. It's 0.4631, which is again greater than 0.05, which is, the alpha or the significance level that we have defined before. And this means that the variances of the two groups are equal. So we have satisfied the assumptions for conducting the independent t-test, the parametric test. So we are going to conduct that test, and this is the code that it will run that test. So this is the t-test. I use the two groups, and then I will save the result in this variable that I call statistical test. So let me conduct or run this piece of code. So as you can see here, our conduct the Welch to sample t-test, and Welch here actually corrects if there is any differences in the variances. So if the variances are not equal, then this wedge creates sort of a correction to correct that. But anyway, we have seen that the variances are homogeneous, so that's not a problem. So here we can look to the p-value. The p-value of this test is, as you can see, is smaller than 0.05. And this means that there is a difference in the mean between the two groups. And in this case, as we have seen also that in the first group, the mean value is 65.9060, and in the second group, it's 82.2536. So this means that using actually models is, it improves the quality of the software, and this is actually different from the second setting when we are not using software models. And this difference is actually statistically significant because the p-value is less than 0.05. Very good. Here, if we don't satisfy the assumptions of a normal distribution and then the homogeneity of variances, then we have to run the non-parametric version of the independent t-test, which is the Wilcoxon rank sum test. So this is the code only here in case that those assumptions are not satisfied. Now we have to calculate the effect size of this difference, and here we have the formula to calculate the effect size for the parametric test, the independent t-test, and the paired t-test. So as you can see, the effect size equation is here the following. So it's the square root of square t divided by square t plus df. And to calculate the t, which is the t statistic, and the f, which is the degrees of freedom, we have these formulas. So I call the test that I've conducted statistical.test, and then I fetch this variable and then the first let's say parameter in that variable, which is the t-test, and the same for the degree of freedoms. If you don't want to use these formulas, you can also look to the t-test that you have conducted before, and here, as you can see, this is the t statistic, and this is the degree of freedom. So you have the values already when you get the output of the independent t-test. Very good, but just to see the effect size, so we have this formula, and we are going to round the effect size to 3 decimal places. So just let me select this piece of code, and I will run it. And as you can see here, so this is the t statistic, this is the df, the degree of freedom, and here we have the effect size, which is 0.752. And according to our specification, this is a large effect size because it's more than 0.5. So this is also the code if you would like to see the effect size of the non-parametric versions. So when you run the Wilcoxon rank sum test and the Wilcoxon signed rank tests. And again, here the equation for calculating this the effect size, as we have seen in the slides, is r equal to z divided by the square root of n, where z is the z-score and n is the number of samples or the observations. In this example, we have 25, and then again you will round the results to 3 decimal places. So that's only for you in case that you would like to see the effect size for the non-parametric test, in case that you have not satisfied the test of the normal distribution and the homogeneity of variances. Very good.